Today, today we are going to have Dr. Zhiyuan Geng to speak. Zhiyuan is currently is this global visiting assistant professor in Purdue. He received his PhD from Crown Institute, NYU, and working with Professor Fan Hualin. And today he's going to talk about asymptotics for 2D Allen-Cahn minimizers. So Zhiyuan, I turn to you. Okay.
So thanks for the invitation. I'm very happy to have the opportunity to speak at the virtual PD seminar. So today I want to talk about two-dimensional Allen-Cahn minimizers. And so in particular, will focus on the triple junction solutions. So here is a problem. So we consider a two-dimensional domain omega, a strictly convex smooth domain. And we consider the energy functional. So there are two parts, the Dirichlet energy and this potential energy. So basically, this U is a two-dimensional vector value function. And we can regard this U as kind of some parameter for material or for a substance. And this potential energy will penalize the distance of U to the least energy state, or sometimes we call energy wells. So here, this WU we assume is non-negative. It's a potential function and vanishes at this isolated points. Okay, A1, A2 to AN. And this AN are two-dimensional isolated point, and we call them energy wells, or sometimes we call them phases. Okay, they represent the different phases of a material with the same least energy, potential energy. And here, this is our Euler-Lagrange equation. It's an elliptic system, nonlinear elliptic system. So we consider the boundary value problem on the boundary of omega. So here is our profile for the boundary. So we assume U naught epsilon is uniformly bounded, and its derivative, tangential derivative, is also uniformly bounded by a constant over epsilon. And basically, U naught epsilon is a modification of this U naught. As epsilon goes to 0, you converge to U naught. And U naught is a bounded, it's a function of bounded variation. Take value only on this finite set, on the finite set of energy wells. So here on the right figure, we can show, so there are several arcs. And on each arc, U naught is just a constant. And so that we have W, the potential energy is 0 on the boundary. And so here for U naught, we have a sharp transition between the different phases. And U naught epsilon is kind of a modification of this sharp transition. So in a order epsilon neighborhood. Okay, so that's the variational problem we consider. So here, we assume some assumptions on this potential. So C2 function equals to 0, the minimal value at the several point. And near each energy well, we assume is not degenerate. So the Hessian matrix is positive definite. So we have the quadratic growth near the energy well. And the second assumption, we look at any two phases, AI and AJ, and we look at the phase plan. We assume there exists a geodesic in the metric induced by this Allen-Cahn energy. Okay, so this capital Uij is a path on the phase plan connecting AI to AJ with the least energy cost. And that energy cost is one-dimensional Allen-Cahn energy. And we just assume the existence of this minimal connection between, and it's called the so-called heteroclinic connection between any two phases. And for the third, and also this minimal energy cost to travel from one energy well to another energy well, we denoted by sigma ij. So the third assumption is on the sigma ij. So we assume two situations. The first situation, we only consider 3 energy well. Suppose if we only have 3 energy well and sigma ij, we assume it satisfies this triangle inequality. So that means if you travel from AI to AJ, the energy cost is less than if you first go to AK and then go from AK to AJ. Okay, and here we require the strict inequality. So that's the first situation. The second situation, we consider more than 3 phases, okay, any capital N, but we require all the sigma ij are equal. Okay, so in the next slide, I'm going to show why we have this assumption on the sigma ij. So here we introduce this minimal partition problem, which is actually the gamma limit as epsilon go to 0. So that's the limit problem. So we consider this U is boundary value BV function. BV function take value only on this finite set of energy wells. And so the pre-image of each AI is denoted by this SI. So this SI will give us a partition of this domain omega. And the minimal partition problem is we minimize this energy functional, which we calculate the measure of the interface between Si and Sj, and we multiply this weight, sigma ij. So that's a weighted sum of the interface separating these subdomains. And that is energy for the minimal partition. And here we also consider the boundary, Dirichlet boundary condition, which U equals to U naught, which is the boundary data, Dirichlet boundary data we defined in the first page. So of course, this is in the sense of trace for BV functions. So for this minimal partition problem, the structure of the sharp interface is very clear. And so the previous result was stated by Frank Morgan in the study of immiscible fluid. And so in Morgan's version, this theorem is studied for each subdomain has fixed volume. Okay, and here I used the more recent version by Mike Novak, who studied the Dirichlet boundary condition, okay, of this minimal partition. So for the minimal partition, the interface are just line segment. And the line segment will end either at a boundary discontinuity, so that's a discontinuity point for U now, or at the interior triple junction. So that's somehow a complete classification for the sharp interface. And at the interior triple junction, this angle, this opening angle of the 3 sector will satisfy this so-called Young's law. So that's a stability for the opening angles. And that's easy to get if you just do a local perturbation and we see calculate the first variation of this energy functional. So, and here, actually this structure is guaranteed by the third assumption. So that's why we assume this assumption, because in these 2 situations, only triple junction is minimal. Okay, only the junction of 3 phases could appear. So otherwise, you can imagine if you have a 4 junction. If you have a 4 junction, and suppose this diagonal, for example, 1 and 4 and 2 and 3 are very, very small, then you could have this 4 junction is also a minimal set, right? It's also a minimal cone. So that's why we don't consider general sigma ij. We require either all sigma ij are equal or we only have 3 phases. So we're only interested in this triple junction structure. Okay, so that's a limit problem. And the minimal partition and the Allen-Cahn epsilon problem is connected by this gamma convergence technique. And that's also a classic technique in the study of Allen-Cahn function. In particular for scalar Allen-Cahn, that's a classic result by Modica's argument. So here there are several different versions in different settings for this vector value problem. And here I also use the recent version by Gazolis on the Dirichlet boundary condition. So basically, the 2 problem is G epsilon, the functional for Allen-Cahn vector Allen-Cahn will gamma converge to this minimal partition, the energy function. And also the minimizer, the U epsilon with the boundary condition U naught epsilon will converge to this minimal partition with delicate boundary condition in L1, in the L1 topology. And also the energy, the minimized energy will also converge to the energy of this weighted sum of the interface, of the one-dimensional measure of the interface. So here, so that means for epsilon small, we have the big picture of this minimizer. Okay, what the minimizer looks like in the large scale. But there are some limitations for the gamma convergence theory. So first, we don't have a rate of convergence. So for example, if we look at not for the convergence of the minimizer, or even for the convergence of the energy. Okay, we only know the first order energy is given by minimal partition, but what about next order energy? The lower order energy, we don't know. So at least we don't know from the gamma convergence. And also, if we want to zoom in the singular structure, like the interface or the junction of three faces, we do the blow-up limit, the gamma convergence cannot give us the detailed profile in a small neighborhood of the sharp interface. Okay, so, and the third one actually is a general obstacle for the Allen-Cahn system, for vector value Allen-Cahn, compared to the scalar case, is that we don't have a monotonicity formula. Okay, for the scalar case, the variational approach is we have modica estimate, which means this energy can be bounded by the potential energy. And then with that, we can get the monotonicity formula, and with monotonicity formula, we can show that the interface is kind of, in the limit case, is flat, and we have the clean out lemma. And basically, the whole theory is built on the monotonicity formula. And for the scalar case, the modica estimate, there are some counterexamples to show the modica estimate may not be true. Okay, for at least for critical point, is not known. So that means for the variational approach, we need to have some novel ideas for the system case. Okay, so here I want to mention a related result by Betul. So his study also a two-dimensional problem, the critical point of the system, not necessarily minimizing. And he can generalize some result from the scalar Allen-Cahn to the vector Allen-Cahn. So this paper is published on ACTA. So he can show that there is a one-dimensional subset gamma, which is a sharp interface. And the gamma can separate into singular part and regular part. So singular part is small, one-dimensional measure 0. And regular part is one dimension, and it's locally just flat. It's a segment. And away from this sharp interface, you will uniformly converge to different faces. And also, he can get this energy. Actually, part of the energy, the potential energy, will converge to some measure concentrated only on this sharp interface. And that will give a stationary variable for the sharp interface. This is energy density. So basically, this work, the analysis depends on the pure elliptic argument, okay, PDE argument. So because the variational approach does not work. And also near the critical point, let's see, near the singular set, what's the behavior near the singular set? What's a blow-up profile is not known. And even at the sharp interface, if we want to blow up to see the detailed profile near the interface for U epsilon, is still open for this case. And actually, for critical point, the solution near the sharp interface could be wound. Okay, you could have this oscillatory solutions for the vector case. So that's quite different from the scalar Allen-Cahn. But in our case, in our problem, we can see a little bit more because we are consider minimizers. Okay, so actually in our approach, the argument is pure variational, and we use minimality a lot. Okay, so here we consider for any blow-up center X0, we consider this blow-up map U epsilon. And this is a scaling epsilon. So that basically that maps the disk of epsilon radius to the unit disk. And as epsilon go to 0 along subsequence, it will converge to this solution defined on the whole two-dimensional plane. And it's also minimizing, okay, because we just rescale the minimizer for U epsilon. And so that will be a minimizing. Locally, on any compact set, it will minimize this energy, the Allen-Cahn energy functional, subject to Dirichlet boundary condition. So we want to study the behavior of this entire solution, the blow-up map, and we want to classify all the blow-up map in terms of their behavior at infinity. Okay, so that's the problem we study. So we want to characterize all the entire solution, and actually that depends on our blow-up center, the choice of blow-up center. So to classify, we consider its blow-up at infinity, so we consider its blow-down limit. Okay, U is an entire solution. So at R goes to infinity, it brings back the large disk with radius R back to the unit disk. And so the limit will be the tangent map at infinity for this entire solution. And we expect this tangent map at infinity will be a triple junction. Triple junction means you have connect these three faces. If we carefully choose the blow-up center near the junction of the three different faces for the U epsilon problem, and if we choose the blow-up center near the interface separating two faces, we expect our blow-up map at infinity will behave like a two-phase solution. So that's like the for the scalar case. Okay, you get a straight line separating two faces, and if we blow up near the interior of a face, for the blow-up limit is just a constant. Okay, so that's the expected behavior we want to prove. So here, okay, so this figure shows the candidate for the blow-down limit of the entire solution if we blow up near the triple junction. Okay, so basically that's just a triple junction. Imagine you have on the whole plane separating into three sectors, and with opening angle satisfy the stability condition, and that will give a minimizing partition of R2 that minimizes energy function. And actually, in the special case, our second situation, if we consider all the sigma j equal, all these opening angles are equal, so we have a so-called equipartition. So that's the so-called Y-shaped minimal set on R2. Okay, so that's a candidate for the blow-down limit. And now I want to introduce some previous result. So most previous result to try to construct some entire solution of the Allen-Cahn system with a triple junction structure at infinity will use some symmetry assumptions. Okay, so previous result depends on the symmetry. So the first kind of result is by this work by Bronsted, Gui, and Schatzman. So they consider the potential is invariant under this symmetry group of equilateral triangle, and also the solution is also within this symmetry of the equilateral triangle. Under that assumption, they can show the existence of the entire solution, and they can characterize some properties of the solution. And later, recently this work was generalized, only assuming the symmetry of rotational invariance. Okay, because for equilateral triangle, besides the rotation invariance, there are also reflection invariant. Okay, so that can be relaxed. And also the similar idea can be generalized to the three-dimensional problem with a four junction. Okay, imagine you have a symmetry of Taylor-Hadron. So the center point will separate the Taylor-Hadron into four identical subdomains, and one can construct a solution resemble that structure. So the problem for all these constructions is only consider all the solution U belongs to the symmetry class. So And it's only minimizing within that symmetry class. So it's not known whether these solutions are stable under general perturbations. Okay, even locally stability, like if you calculate second variation, it's not known if it's positive. So, and for our objective is we want to construct a solution that have the triple junction structure at infinity and without any symmetry assumption. Okay, so now I'm gonna start our result. So we look at this toy model. So that's a simplified model for our for the original Allen-Cahn problem. So the equation is the same. The domain is simplified. We just consider the unit disk, and the boundary condition is also carefully designed. So we design this boundary condition to resemble this triple junction, minimal partition. So we assume there are 3 arcs. Each arc, suppose sigma ij are all equal. So we consider this case, but it can be generalized to general sigma ij. So suppose sigma ij are equal, so we have 3 arcs of 120-degree opening angle. And on each arc, U is the boundary condition. We just take the constant, A1, A2, A3. And these arcs are connected by order epsilon small neighborhood. And with that boundary condition, we consider the minimizer U epsilon, and we define this so-called diffuse interface. That is where the minimizer is away from all the 3 energy wells. And we want to describe this diffuse interface. And we want to find some point near here. And then we do the blow up, we get a non-trivial entire solution which has a triple junction structure at infinity. Okay, so that is a special boundary condition and special domain we start with. Okay, so we expected this diffuse interface will be very close to the sharp interface, okay, in a small neighborhood. So that's our first step. So we can derive the energy upper bound and lower bound for the minimizer, given that nice boundary condition. So here you see this major term, the main term in the solution, in the energy bound, is just the minimal partition energy. And the next order, we can get some estimate in terms of epsilon. So here in the upper bound, we get is just a constant of epsilon. So in our first result, we can only get the lower bound is epsilon to the power 1/2, but later, using some argument we proved later, we can actually improve this to also epsilon. So actually, we can get a sharp energy lower bound and upper bound. Okay, so that's the first step, and that gives more information compared to the gamma convergence. So the upper bound is straightforward. We just construct the energy competitor, and we explicitly calculate the energy. Okay, because here you have this nice boundary condition, so you just build your solution near the small neighborhood of the sharp interface, and near the neighborhood of interface, you just use the one-dimensional minimal connection because we assume they exist. And outside, you just take to be A1, A2, A3, almost a constant. And you carefully design the boundary layer so that we can get the desired upper bound. So that's straightforward. But for lower bound, here we need some non-standard method, but elementary, but quite technical. So we want to find the decomposition of the domain. And on each domain, we can estimate the energy from below using slicing argument. So just slicing, one-dimensional energy. So here is an illustration, this figure. So suppose we have a Y star. So Y star is a horizontal line. And on this horizontal line, most point is either A1 or A2. And suppose we have a vertical line on which most U is close to A3. And then with this decomposition, we can do the slicing argument, because if you look at the upper half domain, upper half disk, we have each horizontal line will connect A1 to A2. So that will give us energy sigma 1, 2. And here on the bottom left, we have in each direction, you connect A1 to A3. and that will give us an energy sigma 1, 3. And here, similarly, each line will connect A1 to A2 to A3. So that's a sigma 2, 3. So that's a lower energy, lower bound for the energy. But the problem is actually we don't have this interior information on these 3 lines. But somehow, by energy minimality, we are able to find approximately this decomposition. Okay, they are not flat. They may not even be continuous, but we can somehow find this decomposition into subdomains and using slicing argument to prove the lower bound. So that's a rough idea. And now with the lower bound, the next result, we can estimate the location of the diffuse interface. So basically, we can show the diffuse interface is actually, so we call the diffuse interface is where U epsilon is away from A1, A2, A3 at a distance, some positive definite distance. And the diffuse interface is in a small neighborhood of size epsilon to the power 1/4 of the sharp interface. Okay, sharp interface is just these 3 radius. And also away from this epsilon to the power 1/4 neighborhood, we have the distance of U to AI is very, very small, have this exponential decay. Okay, so the second estimate, after we get this localization of diffuse interface, the second estimate is based on just a comparison principle, maximum principle of elliptic theory. So actually this part is the novel part in our estimate. So the idea is also only work for 2D. So I'll illustrate the idea using the figure on the right. So for the lower bound, actually that's a standard technique. So the energy can be bounded from below by the measure of this level set, the integral of the measure of this level set. Okay, we integrate with respect to this gamma. Okay, gamma is the level of this level set. And if on 2D, if you look at this level set, we want to show most of this level set should be close to this minimal sharp interface. And suppose you have some large deviation of this level set from the sharp interface, then in 2D, you have to go out and then go back. And that will generate large one-dimensional energy, okay, because we are estimating the one-dimensional measure of this level set. And that gives some extra energy to the lower bound. And then you add this extra energy to the lower bound, you compare with the upper bound, because we have a small gap between the lower bound and upper bound. And that can give us, we can show that for such level set with this sharp, with this large deviation cannot be a lot. Okay, and the measure of such level set can be controlled by this epsilon to the power 1/4. Okay, so that's the idea. And actually, this idea only works for 2D. So now with this localization of the diffuse interface, we are not satisfied because you see this distance of the diffuse interface from the sharp interface is epsilon to the power 1/4. But what we really want is epsilon, is the information within the epsilon neighborhood, because we want to do blow up. So here, the next result gave us some information in the O epsilon size neighborhood of the sharp interface. So that's a result. So we look at this level set, okay, and that can be, so this capital gamma I, and that is on the boundary of the diffuse interface. Okay, this U, the distance to AI equals to gamma. And we can show that for each gamma I, its distance to the union of other gamma J is at most epsilon. So if we look at these 3 lines, the red line, green line, and the blue line, so each point on the right line is either epsilon close to a green point or is epsilon close to a blue point. So that's somehow using that, we can show the width of this diffuse interface is at most order epsilon. And using that, we can get, we can use that to show that our blow-up center, our blow-up limit must be a triple junction. So that's our first result. So combine all this estimates, we can show, we can exist an entire minimizing solution on the whole plane, and the sequence RK goes to infinity, such that along this sequence, this blowdown limit at infinity will converge to a triple junction map. Okay, triple junction is just this partition, Y-shape minimizer. So that's our first result. And here I'm gonna briefly illustrate the idea for the proof. So just based on the previous estimate. So the first step is we find one point such that its distance to the, we focus on this right curve. So that is where U is close to A1. And we know for every point is close to a green point or close to a blue point. So we can find one point is distance to the green point and equals to the distance to the blue point. And that is our triplet point PQR. So they are close to A1, A2, A3, and their pairwise distance is bounded by epsilon. And that is our blow-up center. So we can choose either one to be our blow-up center. And once we blow up, we bring the epsilon neighborhood to the O1 domain. We can see all the three phases, A1, A2, A3. And to get a non-trivial solution at infinity, non-trivial blowdown limit at infinity, only one triplet of points is not sufficient. We actually need a sequence of A2 point and A3 point and A1 point. So that's basically, that's a picture we have. We have a sequence of points, sufficiently many points on any large domain, J epsilon. Okay, J goes to infinity, so that that means at any large scale after blow up, we can always see A1, A2, A3 phases in our blow up limit. And then we can use that to say this blowdown limit must be a triple junction. Okay, must have all the three phases. So that's our first existence for this triple junction solution without symmetry assumption. So roughly at the same time, there is similar work by Sandia and Sternberg. So they studied the problem under different setting. So actually their result, they assume this heteroclinear connection capital Uij is unique. And they can prove a slightly stronger result. So they show that for any sequence Rk goes to infinity, this blowdown limit must be a triple junction. Okay. But this triple junction might depend on the sequence. So along different sequence, you could have different triple junctions. Okay, so that means this could be some spiral at infinity. Okay, so their technique is based on this observation that the energy for the potential energy and the delineated energy, they are not equal, but they are very close. Okay, so it's almost energy equipartition property. So they can show the difference of this potential and delineated energy of small order, okay, R to some power less than 1. And using that, they can prove that this energy density is almost monotonicity. So that's an almost monotonicity formula for the half of the energy density. And using that, they can derive, so any blowdown limit must be homogeneous, okay, must be homogeneous, radial invariant. All right, so now the natural question is, we expect our blowdown limit is unique, okay, because we are considering minimizers, and this spiral profile for the interface is not expected. So, and that was confirmed in my second paper. So basically we show that for any R goes to infinity, this blowdown limit will converge to a unique triple junction. So that means you get this triple junction at infinity and does not depend on the sequence. Okay, so that's somehow the uniqueness for the blowdown limit at for the tangent map at infinity. And one consequence is we can, using that, we can improve our previous energy lower bound. Okay, so here is a rescaled version for the previous. We can actually So R is very, very large. If we rescale this BR back to the unit disk, you get this is just a C over R. And so 1 over R is just our epsilon. Okay, so that will give the sharp energy lower bound and the upper bound. So that's an improvement for the energy estimate. And okay, so here I'm gonna briefly explain the idea for the uniqueness. So actually the technique based on our first paper. So for this, because we know along a sequence, U is can be approximated by a triple junction. And then using that, we can actually, for any large R, by Fubini, we can find an R null that on this circle BR null with radius R null, U is almost the triple junction on this circle. So has a well-behaved boundary condition. So that satisfies the energy along this circle is almost 3-phase transition along this circle. And also we have 3 arcs. On each arc, U is almost A1, A2, A3. And they are connected by a small arc, okay, whose measure can be uniformly bounded. Okay, R now is very, very large. Okay, R in general is very large, goes to infinity. Any large R, we can find this R now. And the C does not depend on R. It's a uniform constant. So now the next step. With this boundary condition, we can perform the similar estimate for our toy model. Because for our toy model, we have this perfectly designed boundary condition. But now, this boundary condition may not be that good, but we can add some boundary layer, do some interpolation near the boundary so that we can have this similar result for the energy bound on this large disk with R null. And also we can localize the diffuse interface in a small neighborhood of the sharp interface. So that's the idea. So we have O in the interior point and also 3 points on the boundary. So here I already consider the rescaled map. Okay, I rescale this large disk back to the unit disk. So then we find this O and the 3 points on the boundary, all depending on R null. So O may not be the center. Okay, O is just determined by the boundary condition. So O is changing. And we take this union of these 3 segments, OD1, OD2, OD3 are the position of the sharp interface. And we can show that the energy is very close to the measure of this 3 segment. And the error is very small. It's a negative power of R null. And also the diffuse interface for the rescaled map is also containing a small neighborhood of the union of the sharp interface. And this distance is also R null to some negative power. And we take, okay, so now we have this 3 segment, we have a partition, and we take this, the map determined by that partition. So we just, on each subdomain, we take U bar R null equals to A1, A2, A3, respectively. So that is U bar R null, we call it the optimal triple junction map at the scale R null. Okay, so that is this estimate for the diffuse interface and the energy. So now we can compare, because U bar R null and U bar R1, if we can find R1 from 2R to 4R, and we compare U bar R1 and U bar R null. And because there's rescaling of the same function, they rescale from U, the same function at comparable scales. So that means if you look at the right figure, so this should be close. Otherwise, if you have the sharp interface here and here, they are very different. For example, this distance of the angle is greater than R null to some negative power. And then you have a contradiction because here in the smaller scale, it should be an A2 point, but in the large scale, it should be an A1 point. So that means that will give us a contradiction. So that shows this optimal triple junction map at a comparable scale at adjacent scales, they are close. And the distance are bounded by this R0 to negative power. And we iterate all this estimate to all the scales. Each time we just enlarge by 2. And we can get, this is a Kersey sequence. And they will converge to some uniform triple junction, to some unique triple junction. And that limit will be our unique triple junction, the tangent map at infinity. So that's how we prove this pure variational approach argument. Okay, so now with that, we can further estimate the asymptotic behavior near the one phase. Okay, so now we already have 3 legs of phase. So we focus on one interface, and we consider along this interface, the solution is actually almost one-dimensional. So that's a result here. And for that, we need to assume the uniqueness of the minimal connection between 2 phases, okay, of the 1D connection. So here is a result. So suppose EIJ is the direction of the interface separating AI and J. It's a ray. Along that direction, as S goes to infinity, it will converge to some translation of this 1D minimal connection, heterocanonic connection. Okay, so and the converge is in a very good sense. So for the proof, actually also based on our energy lower bound and upper bound. So first, we have, suppose this EIJ is just the positive x direction along the x-axis. So suppose for x very large, we know on each vertical line along the interface, the energy is almost sigma. So energy is almost the minimal energy connecting A1 to A2. And then we can have, by the classic result by Schatzman, this on each vertical slice, the UXY can be approximate by some translation of UIJ, of the 1D connection. And this translation, Hx depends on x, is a function of s. And we can calculate the derivative of x. And after some estimate, here I skip some estimate. So finally, we can show this derivative actually is bounded by, on each vertical line, the derivative of the x partial derivative of u. And this actually is almost a radial derivative of u. And that can be controlled by the gap between our energy upper bound and lower bound. Okay, because for energy upper bound, it's just the whole energy, but for energy lower bound, when we calculate the lower bound, we only consider the tangential direction. So we don't consider radial direction. That means actually the radial direction, the integral on the whole plane, is uniformly bounded by a constant. And that will give the integral of this derivative is uniformly bounded by a constant. So that gives a limit of this translation at infinity. Okay, so this also relies on our sharp energy bound. So using the same technique, actually, we can prove if W only have two energy well, 2 phases, the solution is actually must be 1 dimension. Okay, so that's a result. Actually, this result first proved in the paper by Sandier and Peter Slemberg. And also in my work, I can use a different argument, like using this technique to prove this result. So suppose U is an entire solution minimizing, and we have double well potential. And suppose this 1D connection is unique for AI, A1 and A2, then either U is a constant or U is a 1-dimensional solution. And along that direction is the same copy of this 1D connection. Okay, so here I want to point out that if we don't have the uniqueness of the 1D connection, then the U may not be 1D. So, and there are counterexamples constructed by these works by Alama, Bronsart, Gui, and Strassman. So they can show a minimizing solution connected actually 2 heterocanonic connections. So that means in one end is like say UI U1 to 1, and you have on the other end is converged to this U1 to 2. Okay, suppose you have two different connections. So that is non-one-dimensional profile. Okay, so here, further we can generalize all the previous techniques to the half-space solutions. Basically, the half-space solution comes from the blow-up if we blow up near the boundary point. Okay, near the boundary point, and suppose on the boundary we have so we consider U is from upper half plane. It's a minimizing solution of the Allen-Cahn energy. And suppose we prescribe the boundary condition. So suppose here on the positive x-axis is A1, on the negative x-axis is A2. And then we have U, all this blow down limit must be one of the profiles described on the right. Okay, so basically we have this blow down limit. It is unique, and it could be a triple junction, so that there are three phases, or there could be only two phases, but with a boundary layer. Okay, so this case boundary layer, this A3 and the A2 interface coincide with the boundary, or there could be no third phase, just A1, A2, and that's almost one-dimensional solution. Or we could have all the A3, and we have two boundary layers as an interface. Okay, that's all the possibilities. That's a classification for the blow-down limit. And now that would be our final result. So finally, we can get a complete structure for the solution of our most general boundary condition and the general domain. So basically, the minimizer is from large scale is minimal partition. That we know from gamma convergence. And in the smaller scale, all epsilon scale, we know it depends on the blow up position. Okay, if we blow up near the triple junction, carefully choose the blow up center, we can get our triple junction solution. And with the profile, with the configuration characterized by the previous result. So that's a triple junction solution. If we blow up somewhere here, then we can get a two-phase solution. And we know the blow up limit will be just one-dimensional. Or if we blow up on the boundary discontinuity point, we'll get a half-space solution, which asymptotic behavior at infinity is also characterized. And more importantly here, you may find in this profile, there are still some gap, right? So the gap is, suppose near this triple junction point. At O1 scale, we have this is our triple junction. And if you blow up near a small neighborhood, you get a triple junction solution, but this triple junction solution might have some different direction for the interface. And this can be ruled out by the similar technique when we prove the uniqueness. Okay, actually we can show that at O1 scale, it is this direction. And if you zoom in, you get smaller and smaller scale, the direction of the interface will always be the same. And so at O epsilon neighborhood, after blow up, you still get the same direction for that blow up limit. Okay, so that's kind of a neck region estimate. Basically, we show this direction of the interface at smaller scale until if you just zoom in to the large scale is always unique. Okay, so that is our final characterization for the minimizer. So here, lastly, I want to introduce some further open problems. So first is about the symmetry of the solution. Suppose we only assume the potential has some symmetry. Can we say something about the solution? Does solution also have the symmetry? Or at least, can we prove, if we assume the solution is also symmetric, can we prove some stability of that symmetric solution? That's one problem. And also, can we relax the assumption on the sigma ij? For general sigma ij, can we construct, like suppose this is also a minimal junction, minimal set, can we construct such diffuse solutions? And also we can, also in most of our technique, our argument depends on 2D, especially this the key estimate for the localization of the diffuse interface is a 2D argument. Can one generalize to find some new ideas in 3D so that one can construct such profiles for the entire minimizing solution? For example, the triple well potential or even the quadruple well potential to get this so-called T-shape minimal set in 3D. Okay, so that's also a further direction. Okay, so that's all I want to present today, and thank you.
Any questions for Zhiyuan? Yeah.
Yeah, maybe can I have a very quick question? So I mean, you have sort of a complete characterization of 2D. I'm just curious because it's really interesting that if you, let's say you have a compatible profile in 2D, do you have kind of the inverse problem that there's such a model that gives you that profile?
You mean the model?
Yeah, what I mean is that because you go to the picture in 2D?
Yeah.
Yeah.
Let's say this picture.
Yeah, right. So let's say that you are now given kind of a picture with all this sort of boundary and triple junction inside, but you have various number of points. Is there a corresponding like inverse problem that there's such a design for you to see this picture?
Well, so in general, if the boundary is fixed, boundary condition, like you have several arcs, and then this minimal partition is kind of it's not unique, but there are only several let's say finite many minimal partition of this profile, and with that minimal partition, we know if you consider the epsilon problem, the diffuse problem, the profile must look like this. So that's kind of that's our result.
Maybe let me rephrase.
What do you mean the reverse?
So
the inverse?
let's say that you are given an eligible profile. Is there sort of inverse problem question that can you have W and the boundary conditions so that you get that profile?
Yeah, you mean for example, this junction point is first given.
Right.
I haven't thought about that, so I'm not sure.
So I guess which profile can you realize?
Yeah,
from geometric by this fixed field, which one you can realize, I guess.
Yeah. Well, I would say, for example, if all sigma ij are equal, you have all this equipartition. Then probably you take 3 point and you just extend by this triple junction. That will be itself will be a minimal set. It automatically will be a minimal set. So suppose you have this. So there are a lot of freedom here, but I mean, suppose for all the triple junction are just equal, and then this will be a so-called minimal network. It's a Steiner problem, right? Minimal network, and so you can just place your node or junction point in arbitrary way, and that will give a minimal network. And but at least it's locally stable, but if it's global minimality, I'm not sure. So yeah, so I need to think more on that. Yeah.
Thank you.
Yeah.
I guess nobody. Yeah, go ahead.
Yeah, sorry.
Go ahead. Go ahead.
Yeah,
you go ahead.
Again, a quick question. Zhiyuan, so is the minimum partition unique or not unique?
Not unique.
Okay, so if it's
Not
not
necessary. Yeah.
I think you mentioned that we have freedoms to adjust that.
Yeah.
If it's not unique, then the gamma convergence U epsilon convert to that is you mean up to a subsequence or what?
Up to some subsequence, yes.
Up to a subsequence.
And also here is also, I think we need up to some subsequence, but at least you converge to some one minimal partition. Yeah, up to some subsequence. Yeah.
Okay.
So that's But if it is unique, then that's only profile. Yeah, that would be the more rigorous way. So here I cheat a little bit.
Okay.
In this writing.
Okay.
Yeah.
Say up to a subsequence. But do you have examples showing that different subsequence might converge to different minimum partition? Of course, we know minimum partition are unique, but regarding the limit, do you have example showing that the limit might not be unique either?
I don't know.
Okay.
Yeah, I don't know that example. Yeah.
Okay, thank you.
So my question is that are you aware anybody using the flow approach to do this kind of like convergence?
No, the answer is no. I think very few results are available for the flow approach. There are some like for the the so-called calibration. Yeah. And so calibration, they start with some initial data close to this optimal partition, and then they just do the flow and using this paired calibration argument. But this technique, I'm not aware of in the flow problem. Because there are not many literature in that. Yeah.
I see. Okay, yeah. Any more questions for Zhiyuan? Okay, if no question, I thank Zhiyuan for a very nice talk, and also thank everybody. So, all right. Okay, yes.
Thank you, Zhiyuan.
Yeah,
Thank you.
Thanks. Yeah, see you. Yeah.
Yeah,
Bye.
thank you. Yeah, thank you, Zhiyuan.
Thank you.